Hey everyone, and welcome to this explainer. Okay, so today we're diving into something absolutely foundational to the physical world around us, the geometric properties of surfaces. If you've ever looked at a massive skyscraper, a huge suspension bridge, or honestly, even the chair you're sitting in right now, and wondered, how do engineers know exactly what shapes will hold up under all that pressure? Well, it's definitely not guesswork. It all comes down to this hidden geometry of strength. In this explainer, we're going to take the raw, sometimes intimidating math of engineering mechanics and translate it into clear visual principles. We're talking about how simple 2D shapes become the building blocks for massive composite I-beams, and eventually really complex 3D structures. We'll look at exactly how these standard shapes behave, where they balance, and most importantly, how they fight back against bending and breaking. Right, let's take a quick look at our roadmap for today. We're going to start with centroids of standard shapes, then move into the moment of inertia, check out shape resistance formulations, and finally wrap things up with shifting axes. Sound good? Let's dive in. Part 1. Centroids of standard shapes, finding the balance point. Because before we can even think about calculating structural strength, we've got to find our anchor. So where is the exact balance point of a shape? Imagine, for a second, cutting a shape out of a really stiff piece of cardboard and trying to balance it perfectly on the tip of your finger. You know that magic spot where it doesn't tip left, right, forward, or backward? Well, in engineering mechanics, we call that the centroid. It's basically the geometric center of an area, and honestly, locating it is step one in almost any structural calculation. Let's look at how we map this out for a few fundamental shapes. Now, the cool thing here is that our everyday intuition aligns perfectly with the rigorous math. For a basic rectangle, the geometry is just perfectly symmetrical. To find that centroid, which we usually label with the letter G, we literally just go exactly halfway across the base and exactly halfway up the height. It's the ultimate expression of symmetry, right? And it is the absolute fundamental building block for those complex composite structures we mentioned earlier, like T-sections and huge industrial I-beams. And it gets even simpler when we look at the circle. Because a circle is symmetrical in literally every direction, that balance point is defined uniformly by its radius, r. So your x-bar and y-bar are just r. Super simple. But finding this exact center is absolutely critical. Why? Because as we scale up into 3D statics, the Pappus-Guldinus theorems tell us that revolving this simple 2D circle around an axis is exactly how we calculate the volume and surface area of massive cylindrical structures. But things get a little tricky when we lose that perfect top-to-bottom or left-to-right symmetry. Take a look at our right triangle. Notice how the triangle's center of gravity totally shifts? It doesn't sit neatly in the middle anymore. It shifts down and to the left, right toward that heavier, wider base. For a right triangle with base B and height h, that centroid is sitting at b/3 along the x-axis and h/3 along the y-axis. It's a great visual demonstration of a critical engineering principle. Mass and area dictate the balance point. The wider the base, the more it just pulls that centroid right toward itself. So the takeaway here is that as shapes get more complex, the rules of balance follow suit. Just look at the semicircle. Along the flat x-axis, sure, the centroid is right in the middle, just a distance of r. Easy. But finding the vertical balance point, the y-bar, that requires a bit of a mathematical leap. You can't just go halfway up. Because of that curve, the exact vertical balance point is surprisingly complex. It's actually 4 times the radius divided by 3 pi. That exact precise formulation is what ensures the area above that point perfectly balances the area below it. Okay, moving on to part 2, the moment of inertia, the resistance. Finding the center is awesome, but the real world involves physical stress and some really heavy loads. And this brings us to what is arguably one of the most vital concepts in all of mechanics, the moment of inertia, or MOI. You'll also hear it called the second moment of area. But what does that actually mean in plain English? Basically, it measures a shape's resistance to bending. The really crucial point I want to make here is that the moment of inertia isn't just some abstract math problem you solve on a chalkboard. It is literally a shape's structural skeleton fighting back against bending. Think about it. When you stand on a wooden plank, the MOI is the mathematical value that dictates whether that plank holds you up nice and stiff, bows deeply, or completely snaps in half under your weight. Which leads us to part 3, shape resistance formulations, comparing strength. Let's look at how these concepts actually build into concrete formulas. Take a look at this table. Comparing these predefined moment of inertia formulas reveals some massive structural secrets. Let's look at the rectangle. See how the height value is cubed? That means a taller rectangle is exponentially stronger against bending than a wide, flat one. Now compare that to the triangle right beneath it. The triangle's formula divides by a massive 36, which means way, way less resistance. This right here is the mathematical proof of why a solid rectangular beam will vastly outperform a triangular one of similar dimensions every single time. All right, final section, part 4, shifting axes, essential theorems. Because let's face it, structures rarely behave perfectly around their own center of gravity, especially when we start combining them. To handle that, we have two incredibly powerful mathematical tools. The first is the parallel axis theorem. It basically states that the moment of inertia around any parallel axis equals the inertia at the centroid plus the area times the distance shifted squared. And guys, this is absolutely indispensable. It's the magic formula that lets us calculate the strength of complex composite shapes, like when we combine multiple rectangles to form a massive industrial I-beam or T-section. On the flip side, we've got the perpendicular axis theorem, which helps us find the polar moment of inertia, and that's what measures a shape's resistance to twisting and torsion. And that brings us to one final, really fascinating concept, the radius of gyration, usually denoted by a lowercase k. It equals the square root of the moment of inertia divided by the area. Think of this as the ultimate mathematical magic trick in engineering mechanics, because instead of dealing with the complex, spread-out geometry of a shape, this formula literally condenses a shape's entire resistance footprint into a single theoretical point at a specific distance from the axis. It gives you the exact same moment of inertia, but it massively simplifies all those crazy complex structural dynamics. Which leaves us with this final thought. If we can map exact balance points, shift our axes to build composite beams, and mathematically condense an entire shape down into a single point, how does that change the way we design the structures all around us? Well, these invisible 2D geometries are the exact keys that allow engineers to solve massive 3D statics problems. It's how we calculate vector representations of spatial forces, how we balance insanely complex tripods and spatial cable networks, and ultimately, how we build the skyscrapers we live and work in every day. Thank you so much for joining me on this explainer. I really hope you never look at a standard shape the same way again.